Hello, and welcome to the CMCC Mechanochemistry Discussions. I'm Ashley Martini. This seminar series is hosted by the NSF Center for Mechanical Control of Chemistry, or the CMCC. The goal of this seminar series is to bring the community together. The presentations are streamed live on the third Thursday of every month at 10 a.m. Central, where they're available on YouTube Live and hosted for watching later. We have an excellent slate of speakers lined up for 2021, a few in the past, today's presentation, and a couple more in the future. Before we get started, a great big thanks to Dr. James Batiste, the director of the CMCC, Jennifer Belsick, the center's administrative coordinator, and 3 students who contribute to the seminar series, Noah Sheehan, Sergio Romero Garcia, and Quintarius Moore. Thank you so much for joining us. Please do subscribe and follow us on YouTube at CMCC Mechanochemistry Discussions and also on Twitter. One last quick thing, a note that the seminar is being recorded. If you have questions, you can email them to us at cmccdiscussions@gmail.com, and we will migrate them to this speaker to be answered at the end of the presentation. Alternatively, you can enter your questions into the comments on YouTube. However, note that we do reserve the right to remove comments if necessary. Finally, I'm really pleased to introduce today's speaker, Dr. Chris Pickard. Dr. Pickard is the Sir Alan Cottrell Professor of Material Science in the Department of Material Science and Metallurgy at the University of Cambridge. Previously, he was Professor of Physics at University of College London, Reader of Physics at University of St. Andrews. He has held both EPSRC Advanced and Leadership Research Awards, and is currently a Royal Society Wolfson Research Merit Award holder. He's a lead developer of the widely used CASTEP code and introduced both the GitPaw approach to the prediction of magnetic resonance parameters and ab initio random structure searching. In 2015, he won the Raleigh Medal and Prize, the Institute of Physics, awarded for distinguished research in theoretical, mathematical, or computational physics. Today, we're very pleased to have Dr. Pickard here to present on stochastic sampling of material structure space.
Okay, well, thank you, Ashley, for that introduction. So today, my title is Stochastic Sampling of Material Structure Space. Really, this is just a slight change of a title of talks that I've been giving for many years now, about using random structure searching to predict new materials, particularly at high pressures. So my funding comes from a variety of sources, from the mostly the EPSRC, and you can see at the bottom there, I'm also funded by the FutureCat project, which is a part of the Faraday Institution in the UK, which is focused towards developing new battery materials. For the purposes of this talk, I'm not going to be talking about battery materials, but the tools that we're using have very wide applicability. I mean, at root, it's about figuring out how atoms are arranged in space using computational methods. And given, I'm sure all of us listening to this talk today, think about science from the atoms upwards. But for this audience, mechanochemistry, well, this is a phrase that I hadn't really come across very much myself before, but when I thought about it, I suppose that is what I've been doing all along theoretically. So high pressure physics, and I note from some of your previous speakers, is clearly a kind of mechanochemistry. I come actually originally from a condensed matter physics background, and that's why I've got condensed matter exclamation mark here, because the computation is extremely condensed matter, to the point where maybe the physics is taking over from the chemistry. And I think that's embodied in the expression here for enthalpy. So the arrangements of atoms and the reactions between atoms is controlled by energy, but in the presence of a pressure, an external pressure, then the thermodynamic variable that's the most important is the enthalpy. And this enthalpy is a simple expression. It's the internal energy U plus P times V. Now, P is the pressure and V is the volume of the sample. And you can think of this as a penalty function. It's penalizing structures with high volume, or favoring structures that are made dense. As P gets larger and larger, obviously its relative importance compared to the internal energy and the traditional driving forces of chemistry becomes greater and greater. So for modest applied pressures, for example, a few gigapascals, I've got on this slide here a range of different experimental techniques for probing pressure. So on the far left-hand side, we have a large volume press, and this is Paul Macmillan's press at UCL, and this can reach about 10 gigapascals. And the kind of chemical changes that can be induced by that kind of those kind of pressures is largely the squeezing out of space in open structures. So if you've got an open hydrogen bonded lattice of, for example, ice, 10 gigapascals will completely squash and make dense that ice. On the row above, I've indicated some sort of geophysical or astrophysical objects that might correspond to these different pressure ranges. So in the 10 gigapascal range, this might be very relevant to, for example, the moons of Titan, some of the moons of the gas giants in the solar system. As we move to higher pressures, for example, those that you might find near the center of the Earth, around 100 gigapascals, those can be reached using diamond anvil cells, so much smaller volume size than we would have before. And actually, this is where a lot of the structure prediction.
Chris, I'm sorry. Excuse me to interrupt you, but we just realized that your slides are not progressing. So we're still looking at your title slide.
Oh, I don't know why that is. Okay, I've gone back and forth again.
Oh, no, it seems to be just the title slide, which is a good one.
Okay, so how should I do it? Should I stop the share and re?
Give it a shot.
Start it?
Sure, give it a shot.
It's sharing. Can you see it now?
It's still the title slide.
It says, okay, it says sharing is paused. Bring your shared window to the front. Maybe I should stop it and start it again. Okay. Let's go. So what?
Oh, now we see. Oh, okay, that looks promising.
Do you see it now?
Move forward one.
On Zoom, it shows something I've never seen before. Sharing is paused. Bring your shared window to the front. And I'm clicking on that. Why would it? Let's try resume share. I'm clicking on resume share. It's not. It did work in the.
Well, in the worst case, we could have you run it through not in presentation mode. You want to try
when
that?
It's not in presentation mode, has it changed now?
Not yet. We're still looking at the intro slide.
Still the intro slide now?
Oh, now it's we see condensed matter, a blue slide.
Okay. Well, maybe we should just do. How about doing it this way?
Let's do it this way. At least we can move forward. Sorry about that. I should have notified you earlier, but if you could.
Well, I guess you didn't realize that it. Unfortunately, on. There we are. You've got to use those buttons. Okay, right. Okay, shall I just carry?
So let's move forward one, and let's just make sure that works before we do that. Okay, perfect. So now that's working well, and we see the slide that says structure prediction. And back to you, Chris.
Yeah. Okay. So back to condensed matter. So so you heard me introduce condensed matter, and I got to the center of the Earth, and pressures of around 100 gigabars or 100 gigapascals or a megabar. So these pressures can be explored using diamond anvil cells. These are difficult experiments to do, typically involving small volumes of material, and so offered a great opportunity for theoretical methods to help understand what the properties of materials and structure of materials might be. So it's much higher to find something new if you try to make predictions in an area that's difficult to do experiments than one that's easy. So I noticed that you've had a couple of talks from high pressure theorists and experimentalists in this series already. And so in order to maybe show you something a bit different, I've decided to focus on what I think will probably be much higher pressures than they have been discussing. And this is where we're getting to the point where where you might think that physics is starting to crush chemistry, and this PV term is dominating. And so these are, as you get to the pressures, oh, hang on. What's going on there? Okay, pressures above around a terapascal, you have to use different experimental techniques. One of those involve using laser shock physics, and this is the small picture here in the center at the bottom is the core of the National Ignition Facility in Livermore, which allows through shock physics to probe the terapascal range. From a astrophysical point of view, these are the pressures that you might experience at the center of Jupiter. Now, as you go further to the right, we see sort of a menacing nuclear explosion, and on the far right, part of the Large Hadron Collider. And I added those on just to set the scale for pressure. I mean, pressure, you can keep increasing pressure. It goes, you know, so terapascals and petapascals, and then on the far right, which I've tried to translate the kind of pressures, the equivalent pressure of the closeness of the particles that are being squeezed together in the Large Hadron Collider. So as they're being collided together, it's equivalent to making a very close approach between particles. And this is on the 10 to the 98 petapascal range. So there's a huge range of pressures that we might want to try to explore the properties of matter for. From an astrophysical point of view, as you go beyond stellar pressures, you start to worry about those on the surface of neutron stars and then into the into neutron stars and white dwarfs. Now, as I mentioned, the experimental techniques are very, very difficult, and so it turned out to be very useful to develop theoretical techniques that allowed us to anticipate how those materials might be, how the atoms might be arranged at these very high pressures. Now, when I started work in this field, structure prediction existed. It was considered maybe for molecular crystal polymorphism in the pharmaceutical industry, maybe in some inorganic materials. But mostly this was using force fields and model potentials. The big difference of the work that I introduced, and there are others at the same time, in particular Artem Oganov in the early to mid 2000s, was approaching this purely from first principles. So using the basic rules of quantum mechanics and density functional theory to calculate those energies that are crucial to this structure prediction. So in principle, structure prediction applies, to molecules. Protein folding is in principle a kind of structure prediction, but obviously much more challenging due to the numbers of atoms involved. For my purposes, I'm mostly interested in predicting the structures of crystals or defects in those crystals, and they might be point defects or interfaces. So as I mentioned, in the early days of structure prediction, people used what you might call an interpolative theory for the energies, which will be empirical or empirical force fields. In the modern language, this might be called data-driven or machine learning, and I'll come back to that shortly. The breakthrough in applying this to very high pressure was the use of first principles methods. And this actually turned out to be useful, one, for an obvious reason that because these very high pressures hadn't been explored before, the potentials didn't exist, but also, as I'll mention in the next couple of slides, made the problem somewhat easier. So if you use a first principles method, it's a extrapolative approach. It's based on quantum mechanics. As far as we know, quantum mechanics will work in extremely under these extremely high pressure conditions. And the particular flavor of first principles methods that we were able to use was density functional theory. So density functional theory is an approximate method, but it's based. It can be based on solid theoretical groundings, which means that it should apply to a wide range of conditions. In fact, there's good reason to believe it gets better at very high pressures when you compress and make the charge densities more uniform. So the second reason why a first principles approach turned out to be a good one, in addition to its robustness and applicability, was that it meant we were dealing with the true energy landscape, or closer to the true energy landscape, rather than the sort of empirical energy landscape, which tends that the empirical potentials were fitted or adjusted so that they're good around the minima of the the landscape, but weren't telling you very much about the higher reaches. Now, if you're going to start sampling and structure predicting, you want to know the energy landscape accurately throughout that throughout the configuration space. So using the true first principles energy landscape, which is based on Coulomb's interactions and Schrodinger's equation, all soft and smooth functions, turned out to make the structure searching problem a little bit easier. So although these first principles calculations are expensive computationally, they if you can find your minima that you're interested in more with fewer samples, then actually you can end up winning. And that turned out to be the case. There's a little bit of a twist to the tail, which I'll come to later on. So there's several arguments as to why these smooth first principles landscapes might be helpful. But one of the key features is this feature of a smooth landscape. So here I've got a picture of a one-dimensional representation of a smooth landscape. And what you can see just by looking at this landscape is that there's a correlation between the width of the data of the basin and the depth. And so simply put, if your energy landscape is bounded in the gradients that it can achieve, then if you can't get very steep, then the only way to get deep is to travel a large distance through that landscape. And so this leads to a correlation between the basin size and the width, and this has been well recognized. And just in a 1D example, structures predict finding the global minima would be relatively straightforward, in that you just drop a ball in at random in a few different points and then minimize to the nearest local minima, and within a few samples you'd find the ground state. So David Wales in his Energy Landscapes book and many other publications before have sort of observed these features of smooth landscapes. So at its core, my method for structure prediction is called ab initio random structure searching. And basically you start with a crystal, a periodic unit cell of a random shape filled with atoms placed in random positions, and then you feed it into your favorite DFT code and go downhill until you find the nearest local minimum. And so the forces move the atoms, the stresses change the shape of the unit cell, and when your atoms stop moving, you stop. Now, when I first started doing this, I would then stop and then do it again, and stop and do it again, and then build up my samples in that way, one after the other. But in around 2003, 4, 5 was the time when multi-core computer chips started to become available, and so parallel computation became available to everybody, including myself at home in your PCs that you could build yourself in your bedroom. And so actually the right way to do parallel, and this was the sort of birth both in this area, and maybe you've probably heard about the Materials project and Gerd Ceder's project, which was doing high throughput computation on samples from databases. At the same time, we were doing high throughput computations on samples at random and using that to predict structures. So this method becomes powerful when you start doing this many, many times in parallel. So this 5 times in parallel, but really, you really want to use them in thousands of times in parallel on a large modern compute cluster and generate large numbers of samples, because often the thing that you're most interested in doesn't come up very often. Okay? Most of the time, most of the sample will be uninteresting or largely physical because they're near the bottom of the energy landscape, but not necessarily the most interesting structures. So when you're building these random structures, one key thing is to be sensible in the building of the random structures. So what do we mean? Well, I mean, to start with, don't put atoms on top of each other. If for example, you used a model Lennard-Jones potential and you put the atoms on top of each other, they'd ping apart in a second in any minimizer. In a first principles DFT code, if you put atoms on top of each other, often you get complaints from the minimizer. It doesn't like it too much. So just don't put them exactly on top of each other, put them an angstrom apart or whatever. This is kind of equivalent to what's known as a Poisson disk distribution to start with. So it's not a pure random sampling in the sense that the atoms could go anywhere. They're drawn from a distribution such that the disks or spheres don't overlap. So this spaces the atoms out a little bit better. You also want to choose roughly the right volume for your unit cells so the atoms can see each other, so they can come together if they want to bond and so on. So yeah, you've got to decide the density of your unit cell. Very powerful ideas are also to impose ideas such as chemical ideas, such as molecules, fragments, distances, and connectivity. We use this a lot. Also, we make big use of symmetry, because most crystals have some degree of symmetry, and this can speed up the searches considerably. Incredibly useful approach is to actually work with experimentalists, and if a structure has been partially solved, say you've indexed a powder diffraction pattern, you know the shape of the unit cell, that can rapidly speed things up. So just to show you an example of what we call these random sensible structures, on the left-hand side, I've shown a unit cell of sodium niobate, and I've indicated all the pairwise differences between all the different species. I then ask, well, let's build a random structure adhering to these minimum distances between the atoms, and that's what I'm showing on the right-hand side. So it's a kind of very geometrical potential, and every sample you get respects those distances, and so looks kind of chemically reasonable to start with, but also has some diversity and allows you to find new arrangements. Of course, the more sensible you make your structures, the more you're steering your search away from completely radical things that you don't think are sensible. So there's this balance between those. So this actually comes into this balance between what's known as exploration and exploitation. So when people are doing global optimization, they often talk in these terms, and I would say I'll hold my hand up and say I'm very much in favor of exploration. So the random sampling type approach is within the constraints of whatever you've decided is sensible, uniformly distributing your samples and pushing out into the corners of your distribution. Whereas if you have a more learning type algorithm, then you're tending to focus on things that you found to be good before and using that more to try and find low energy structures. And they're appropriate for different situations, and you probably, if you're a user or consumer of these methods, you probably want to use, take a range of different approaches to try and do the best job. But for the kind of searches I'm doing, which is largely, trying to rarely find something that's really quite different than people expected before, then I find the uniform sampling from random structure searching very effective. As I mentioned before, the beauty of this method is intrinsically parallel, unlike a, say, learning algorithm, which has to go through generations. You have to go through a generation, learn something, and then go to the next stage. In a random structure search, you can do it all at once in one go. So you can do it on each, if you had 1 million compute cores, then you can do a minimization on each of those 1 million compute cores at once, and then you'll get your answers as quick as it takes one sample to be generated on a single core. Might be quite expensive, but you could do this if you were impatient to get your answers. And because it's random sampling, each sample is uncorrelated with other ones, which means if you keep finding the same structure again and again and again in your searches, it's meaningful. It means that you're starting to saturate your search space. Whereas in a learning type algorithm, if you find the same answer multiple times, then that's telling you that you've learned that's where the answer is. So you can't attribute too much meaning to repeated discovery of structures there. So this gives you a kind of stopping or non-stopping condition. The other thing that I think is very important and useful in random structure searching is the robustness. So there's very few parameters, so you can set the calculations running and just go away and do something else and wait for it to grind and generate the samples. And also, those few parameters that there are the same quantities that a physical chemist would discuss as well in terms of bond lengths and molecular units and so on. So they're very communicable. So this is actually very helpful when you're writing up how do you do the search. Well, we put atoms into a box of this volume, of this density, and we didn't let atoms get closer than a certain amount, and we use these space groups. It's quite easy to explain what you've done. So okay, so now I'm going to see if this works. I've got a movie here, so I'll see if this works in this mode. So just to show what this means. So this is an example of a fixed unit cell search for dense boron, and most samples you do, you'll end up in some high energy configuration. You won't find the true ground state the first time you try. Well, most likely not. And so you'll end up in the peak of the density of structural states. On the right-hand side, I'm showing a density of structural states. So when you relax the structure, you'll end up there. So I'll see if I can show. Is that moving? Yeah, great. So okay, so this was a relaxation leading you to the gray spot in the peak of the density of structural states. So that's where you'll mostly end up. You'll start off looking random and you'll end up looking quite random. But in this case, about once in 200 times when you do the relaxation, you'll end up this situation, starts off looking just as random as it always has. But as you relax, and this is just going straight downhill, so there's no annealing or anything like this, it's a straight downhill minimization. You end up with this beautiful configuration. This is gamma boron made up of a beautiful icosahedra and dumbbells between them. So about 1 in 200 times for 28 atoms a unit cell. It's not too difficult a problem. So this is coming back to the twist in the tale. So I said at the beginning that the energy landscapes for empirical potentials are not necessarily very benign or easy to search using a random sampling approach. And that's what I'm showing here. I've got silicon. The filled in white curve is the density of structural states for density functional theory silicon. And then the gray line and the light blue line are two different force fields, the gray line being the Tursoff potentials. And you can see these density of states don't look the same, structural states don't look the same at all. And indeed, for the Tursoff potential, the number of the chance of you getting a low energy configuration is incredibly low. And so they're all purporting to be silicon, but they're not treating the whole energy landscape in the same way. And so this is showing, actually why I was lucky using density functional theory to do this random structure searching, that the landscape was benign in a way that allowed me to find the ground states. If I tried that with a Tursoff potential, I'd have given up and invented a genetic algorithm or something to try and solve the problem. Now, the twist in the tail is, and no doubt we've all heard a lot about this, is the rise of machine learning in the sciences. So actually, an empirical potential is kind of a data-driven potential, but modern techniques allow you to use a lot more data and a much more flexible functional forms. And in principle, you could learn the whole landscape. So actually, the chance is now that we can look at the whole energy landscape using machine learning, and therefore do searching using effectively empirical potentials. What I said wasn't such a good idea to start with better potentials gets it to be a better idea. Okay, so it hasn't gone to the next slide. Okay, so now I'm going to just show a few examples of applications in the last few minutes. So in the early days of structure searching, both for myself and Artem and Yangming Ma, there were many fantastic opportunities of things to discover. And so we didn't have to try too hard before we found at high pressure structures that just hadn't been anticipated, phenomena that couldn't be imagined before, and some of them that then quite rapidly were confirmed by experiments. So it was kind of a golden age of this field. In the first application I had was to finding good structures for dense hydrides. So there was a lot of interest because Neil Ashcroft had suggested if you mix something with hydrogen, you might be able to get superconducting high temperature superconductors. Now I know you've heard from Eva Zurak, so I won't go into more detail about that, but this is become an even more exciting field with the experimental discoveries that have gone alongside those theoretical predictions. Other predictions we made were for the crystal structures of hydrogen at high pressure, and indeed the structures that I found in my early searches on hydrogen have become the benchmark for most theoretical and experimental structural studies of hydrogen at high pressure now. In terms of mechanochemistry, I think a nice example was the fact that if you squeezed ammonia, well, theoretically, if you squeezed ammonia to around a megabar, there was a spontaneous I observed a spontaneous transfer of protons from one ammonia molecule to another to make ammonium amide. And indeed, some years afterwards, this was confirmed experimentally as well. So this is pressure causing some change in the chemistry of a system. And indeed, one of the very nice results was when we went to even higher pressures, to terapascal pressures, we started to find that even what were thought of as simple metals like aluminium had a volume collapse and became rather complex. So this example here was a host guest phase for aluminium at high pressures. It hasn't been confirmed experimentally yet, but the people at the NIF would be very, or other shock physics facilities would be very happy to be able to find this structural transition in a material such as aluminium. It was particularly interesting because aluminium had been used as a shock standard, And so there were lots of extrapolated equations of states which weren't taking into account the fact that there could be volume collapses due to phase transitions. Okay, I'm having to click my way through here. Okay, so what are we doing now? So those are all fairly old results. The method hasn't changed greatly. Randomly sampling configuration space, relaxing using density functional theory. But what has changed is we've got more and more access to compute. So we can do things that weren't so easy before. And in particular, a real challenge that is fun to be looking at the moment is to start exploring composition space. So the early studies were on a single element or a single composition. Then there was work done on looking at binary compounds. So there's been a lot of work on binary hydrides and so on for these superconducting hydrides. I think the real challenge now is to go to involve more elements. So for example, my work on batteries, you're immediately, if you're looking at a battery cathode with lithium shuttling in and out, you're immediately looking at a quaternary chemical system. And so really we need to be able to deal with quaternaries. And so this leads to two challenges. One is generating enough samples to sample all the possible compositions. So more compute can help with that. But then when you've done it, visualizing or understanding the data that you've got at the end is a real challenge. So the work I've been doing with Ben Shires, he's my PhD student in Cambridge, has been developing what are known as dimensional reduction techniques to allow us to more efficiently visualize data. So what we've got here is an example of a search I did with 1 gigapascal. The data has been is uploaded to the materials cloud, so anyone can have a look at that data set. Ben analyzed that data set using his dimensional reduction technique, and well, it allowed us to visualize the data, which is something, because when you get data, it's just a pile of numbers in files, and so it turned it into a picture we could look at. What we found really beautiful was that without any work, immediately it started forming these tetrahedrons that you'll be familiar for from the quaternary composition space. So this just emerged from the dimensional reduction technique. So what I'm hoping is that these kind of techniques will just become part of the normal workflow of doing a searching of a random structure search. You just should be looking at so anyone who works in data tells you look at your data. So developing tools to allow you to look at your data are central. So on that line, with Andreas Hermann and Lewis Conway, we recently looked at this same carbon, hydrogen, nitrogen, oxygen system, but at 500 gigapascals. So the reason for doing this is that this is a relevant pressure. 500 gigapascals is relevant for deep in Uranus or and other exoplanets. And so what we did is generate hundreds of thousands of different structures using AIRSS and analyze them, and to try and pick out which are the important compounds. And the striking result was that actually there weren't very many, but we were able to find a stable quaternary compound at these very high pressures, and the formula was hydrogen HCNO. And actually, when we looked at this, one of the questions might be, at the start I challenged, is chemistry really happening or not? And at 500 gigapascals, the answer is yes, actually, the octet rule is still working. And if you look at this HCNO compound, it's exactly isoelectronic with diamond. And indeed, some of the polymorphs of this form look just like the diamond lattice. So that was interesting. So we found a true quaternary compound. We've indicated on this plot here the point at which Uranus's composition might be found, and then we can consider which of the nearby stable compositions that composition would decompose into. And what we found is that most of the stable compounds that were relevant were relatively hydrogen poor, so there's not too much hydrogen in them. And we also found that these realistic mixtures, for example, the synthetic Uranus mixture, don't look like they easily decompose into, say, pure diamond or pure hydrogen. And this is relevant to this idea of diamond rain in these planets. So it says something about whether that's likely or not. Now we'll notice we've just done one pressure here. We've done hundreds of thousands of samples, but probably we've missed things already. But what we hope is that this is sort of a statement of intent for the theoretical field, is that we're now starting to hopefully build up databases of mineralogy at pressures where we very difficult to do experiments in the normal way. So we can start to build models, more detailed models of exoplanets. Now, I do want to get to the point where we start to break chemistry. So one of the early projects in this area I did was in carbon. I just wanted to know what is the densest possible form of carbon. And working with my postdoc Miguel Martinez Canales, you know, he was working away, and I said increase the pressure, and he'd go from 100 to 200 GPa, and eventually got up to 1,000 GPa, terapascal. And I just decided, no, let's just go for it. Let's increase the pressures in a logarithmic way. So do 1 terapascal, 10 terapascals, 100 terapascals, 1,000 terapascals, or a petapascal. And he did this, and wonderfully, we found a whole sequence of phase transitions in carbon. Below a terapascal, you'll start to get the diamond structure. As you squeeze it further, it's theoretically known that diamond will transform to the BCH structure. It had been suggested the simple cubic structure was the next phase that it might adopt. But then beyond that, we found the simple hexagonal structure, an FCC structure, which turned out to be an electride with the calcium fluoride structure. And then beyond then, there was a double HCP structure. And then afterwards, finally, at a petapascal, we got to the BCC structure. So if you think about it, you know, carbon is great interest. Even metastable forms of carbon win Nobel Prizes. And Miguel had found 4 new thermodynamically stable phases of carbon. Admittedly, fairly well out of reach of experiments, but possibly important to problems such as laser fusion, because the capsules that are used in the NIF are actually made of diamond-like carbon, or some of them are made of diamond-like carbon. So if they're trying to make laser fusion, they're probably passing through these kind of phases on the way up to very high pressures. So click here. So another area we explored is surprising compounds at these very high pressures. And so this result here, again with Miguel and Bartolomé Montserrat, and much of my work with Richard was Richard Needs, we found that actually iron and helium, so helium being a noble gas element, strongly reacted with each other at above 4 or 5 terapascals. And if you look in the bottom right-hand corner, you can see the scale for the formation energy is multiple electron volts. So it's a really quite strong effect, the binding of iron and helium. And this just simply had not been anticipated as a possibility for any of the models made for cores of these planets. And so while we've shown that it looks like iron and helium will react at these very high pressures, you do have, if you want to try and claim that this is relevant for planetary sciences, you need to have some mechanism for helium getting into the core. Or maybe it's generated through radioactive decay in the core. Anyway, so at these pressures, this is not to do with the octet rule. This is not standard chemistry. It's to do with packing and the strong impact of the PV term. So just to finish off, so I'm in a materials science department. You might wonder why would they have me in a materials, especially the Cambridge Materials Science department is a very, it's called materials science and metallurgy. I mean, very focused on making materials that really matter. I can't get away with just doing high pressure physics at terapascals the whole time. I have to do some more impactful work as well. And actually much of the research that we're doing in my group at the moment are going beyond crystal structures, looking at grain boundaries, interfaces, and so on, and also what we call interfacial materials that are stabilized by deposition on the surfaces. So not exactly related to mechanochemistry, but this is what I'm spending a lot of my time in my group doing. So just to finish off now, it's my conclusion. So some sort of stochastic search, be it a random search or an evolutionary algorithm, to get some randomness in there somehow or other, does and has allowed us to discover many interesting things. Many of them have been subsequently confirmed now by experiment. You know, it's worth taking a step back and thinking about this. I mean, when we started in this field, not a normal situation. Theorists were not, and the computational people were not given much credit for making predictions that turned out to be true. It didn't happen very often. Most of the calculations that were done were based on crystal structures that were known or had been inferred or guessed. but to routinely uncover things that then turn out to be true. This was a new phase for this field. I mean, it's normal in other areas of science for predictions to come true. For example, orbital mechanics, or to some degree, weather forecasting. Okay, but it's nice that it's now found its way into our field as well. For me, I started my research not sure if I wanted to be a theoretician or experimentalist. And what I've really enjoyed about this this technique is it does allow me to do experiments. I can play, I can try, I can do what if experiments, albeit on the computer, and sometimes see something that people have never seen before. So if you would like to have a go at this yourself, the codes I use are widely available and freely available for academic research. So the CASTEP code is a commercial code, but is available for a cost-free license for academic research. And the AIRSS package I use is an open source GPL2 code, so you can just download it and do what you like with it, subject to the GPL license. So I finished now. I'm sorry about the slides. Hopefully the YouTube video will sort that out. And that's the end.
All right. Thank you. We have a few questions from the audience, the live audience. First was regarding the slide on exploring compositional space. There was a question about, it says that the images are indeed beautiful, but can you tell us a little bit more about how you use dimensional reduction and how this connects the 2D and 3D structures shown?
Yes, okay. So dimensional reduction, it's a task in computational science, and there are different ways of doing it. Very widely used are, for example, principal component analysis, which is essentially taking your point cloud in a high dimensional space and twisting it in space until you're getting the maximum variation in your in the number of dimensions you're looking at. So it has the biggest shadow essentially in the space you're looking at. But that approach tends to pile things on top of each other. So for example, if your points were living on a low dimensional manifold, and a manifold is like a high dimensional sheet in an even higher dimensional structure, if it was on a flat sheet, but that sheet was folded, then if you do PCA, you'll end up looking through the sheet and everything will be sandwiched on top of each other. So what we do is what's known as manifold learning. And it's inspired by some, it's a different technique called SHEEP, but it's based in mathematics, is very much based on UMAP and TSNE, which are techniques that are used, very widely used in biology. We had to change it a bit so it properly represented an energy landscape. In particular, you'll notice on these plots here, some of the spheres are bigger than others, and also, you get these sort of bunching of points in space. This is intentional because we're trying to show. So if you did a normal UMAP dimensional reduction, you would end up taking every diamond. Say you found a diamond 1,000 times, then those points would all be collapsed on top of each other. Okay. So what we do is we put little hard spheres around each of the points, so that if they're found 1,000 times, it grows the volume in space. So you can see that there's a big basin there that we're finding very commonly. So the technique we use is manifold learning, and the point of that is, so for example, if you had a folded sheet in high dimensions, it unfolds that, and the way it does it is just by looking at local connections between points, so which points are near to each other. It's sort of a nearest neighbor graph, and then just unfolding that and then putting that down in 2D. So you can choose to put it down in 2D or in 3D. And so hopefully you can see that the 2D, if you sort of squint, the 2D picture also looks like a tetrahedron, but splatted down onto in the third dimension. Now, one of the really interesting results that I didn't go into detail here about was that what Ben has found is that you don't need more than 3D. So it's not, when you're doing dimensional reduction, maybe you need 7D in order to properly visualize the data. It's turned out, at least for the, I'm not sure for the quaternary data, but at least for the elements and the binary data that we've looked at, 3D is enough. You don't get any more from the representation by going into higher dimensions. Now, actually, this is super interesting because this is telling us something about how machine learning might be successful at doing structural prediction, because it's telling you that your structures are living on a much simpler, a much lower dimensional manifold than you might think to start with. And so the task then becomes to sample on that lower dimensional manifold. So that's sort of next steps. But hopefully that answered the question.
Thank you. A related question is the dimensional reduction visualization code publicly available?
It will be. So as you can see here, the paper is submitted, and as part of the submission, it will be available under the I think we'll probably be under GPL2 license. Not quite yet, but will be.
Great. Here's another question. What fraction of the minimized structures end up being disordered versus crystalline? Okay, so it's a difficult question to answer as in the sense that it's defining disorder. So if I'm doing typically the number of atoms that you're doing your searches with, you might do 100 atom searches, but it's not so common. I mean, normally people have got 28 odd atoms in a unit cell. So you might ask the question, how disordered can you get in a 28 atom or unit cell? Now, but when you look at this, can you see the dense boron slide here? Yeah, so you can kind of assess it by looking at the weight in these density of structural states. So I would say the structures in this in the big peak are analogs for amorphous or disordered or glassy-like structures. In this particular case, the volume of that peak, so the volume of structures in that peak to the ground state is about 1 in 200. So the ground state peak is 200 times smaller, something like that, or 100 times smaller. If you increase the number of atoms, the size of the disordered peak will just grow and grow and grow, and the size of your ground state peak will shrink and get smaller and smaller and smaller. And this is why eventually you'll be looking, techniques such as random structure searching, they'll run out of steam. But they kind of have to, because we need the universe to be rich and complex. Everything shouldn't collapse to all be the same structure, otherwise we'd be dead. So it's kind of correct that eventually this runs out of steam and the other possibilities dominate. Great, thank you. Let's do one more. Your work nicely explains the isostatic pressure applied. How about shear? Does your code perform materials discovery under high shear?
That's a fantastic question. So the answer to that is the CASTEP code, which is the code we use. Indeed, you can apply a shear. You can apply a shear. So yes, you can do that. Your challenge. So you could ask CASTEP to randomly make structures relaxed under a certain external stress or strain. Your problem is how do you rank your structures energetically? Because non-hydrostatic stresses become path dependent. Maybe it's probably well known. So it's not completely clear, which is the one that you're going to get. Now, I don't want to spoil any surprise, but this is something we're working on at the moment, and yeah, so there may be an answer to that, but it's not completely clear. So CASTEP will do it, and you'll end up with a bunch of structures, and it will report some enthalpy or some energy. I think you'd have to be very cautious about which one you chose as being your stable composition. But it's a very good question. All right, thank you very much. If additional questions come in, we will forward them along to you. And thank you again for the presentation.
Thank you, Dr. Pickard, for an excellent presentation. And thank you so much for joining us. Please remember to subscribe on YouTube at CMCC Mechanochemistry Discussions. We have an excellent slate of speakers for 2021 already lined up. Here's a few, and there will be many more, and we look forward to you joining us for all of them. Thank you.